There was a time when everything happened. Was it random or a seeming miracle sometimes attributed to the unseen hands of the divine being? Then the Greek and other ancient civilizations began to explore the rationality and logic to explain how the universe works. The paradigm shift came through the likes of Galileo and Newton through the introduction of classical mechanics. The universe was then built as a kind of cosmic clock ticking with mathematical precision where almost every moment and phenomenon could be explained and predicted through the observations and equations. In the early 20th century, this view of mathematical deterministic predictable universe was shattered with the new advent of relativity and quantum mechanics. I repeat, relativity and quantum mechanics. Time was no longer set in stone, and precise location of a particle was no longer measurable. Einstein, Planck, Bohr, Schrödinger led this new paradigm shift. This might seem like end of the story, but there has been one additional, more recent paradigm shift in the development of physics that perhaps did not receive much fanfare, but it is undoubtedly equally profound. And this is how quantum mechanics was supplemented and made more complete by the quantum field theory. It is the basis of the best theory we have in physics today to explain nearly everything, called the standard model for particle physics. So the present attempt is relativistic quantum mechanics. Klein-Gordon equation is a step to Dirac's equation wherein we encounter with antimatter and spin of electron. Actually, we were not aware of antimatter when Dirac's equation was tried, and spin of the electron is an additional outcome of relativistic quantum mechanics. I want to mention that relativity is always not talking about only high speeds and high energy. The perspective for stationary particle also becomes different and more legible when we are discussing it from the relativistic point of view. The immediate questions are: what is quantum field theory? Why it is necessary? How it is different than quantum mechanics? By definition, in theoretical physics, quantum field theory (QFT) is a theoretical framework that combines classical field theory, special relativity, and quantum mechanics. You have started watching this video. I am Dr. Shyamkant Anwane, Professor and Head of Physics Department at Sri Shivaji Education Society, Amravati's Science College, Nagpur, India. To handle this issue of relativistic quantum mechanics, we need a tool, four vectors, that abstracts all facets of special relativity. We shall come out with the Einstein's famous energy-mass relation and collectively explore the quantum mechanical operators to learn what we want to learn, relativistic quantum mechanics. So first thing first, we shall deal with four vectors. Now we shall deal with four vectors in special relativity. The four position x, capital X, we represent by Ct, x, y, z. This can be in short written as Ct and r bar, where r bar is 3 vector. The usual 3 vector we write as r bar is equal to x I cap plus y j cap plus z k cap. In addition to this r, we have Ct that makes it a 4 vector. Now let us define the product of x with itself. it is c square t square minus x square minus y square minus z square, which in general can be written as c square t square minus mod of r bar square, which we define in special relativity as interval s square. Now we can denote this four position x as x0, x1, x2, x3, which correspondingly represents ct, x, y, and z. In general, it can be written as x suffix mu, where the suffix mu rolls over 0, 1, 2, 3 in all four what you call variables that leads to four vectors. Similarly, the observer in another inertial frame S dash represents the same event as X dash, which is CT dash, then X dash, Y dash, Z dash. In general, it can be written as CT dash and R dash. I want you to notice that C remains same in all inertial frames. That is the contention that Einstein has given as second principle of relativity. I guess everyone knows it. This can be written as x0 dash, x1 dash, x2 dash, x3 dash, and in general can be written as x dash suffix mu, where mu rolls from 0 to 3. Now x dash into x dash offers us the same quantity s square, which is c square t dash square minus mod of r dash square. This interval is unchanged for all inertial observers. This leads us to this very equation. Now we shall attach our clock to the origin of frame S dash so that the position of the clock can be represented by zero vector. So substituting r dash equal to 0, we can write, actually we are putting this equal to 0. So c square t dash square is equal to c square minus x square minus y square minus z square. And we can write this as ct dash equal to ct into under root of this very stuff. Now here x square plus y square plus z square we can write as r square, and this overall term r square upon t square we can write as v square. So ct dash is equal to ct into under root of 1 minus v square by c square. So this we can write as dt dash, taking change on both sides. So dt dash upon dt. I'm doing this because we can cancel out c on both sides. And we can write dt dash upon dt is equal to under root of 1 minus v square by c square. Actually, in relativity, we write gamma is equal to 1 upon under root of 1 minus v square by c square. So we can shorthand this to 1 over gamma. So here I have carried that last equation for our convenience. This is a 4 position, and when we differentiate 4 position with respect to the proper time, that is dt dash, we get 4 velocity vector, where u I'm writing as 4 velocity. Now I'm differentiating with respect to time because proper time I am using for differentiation on which all inertial observers will agree. So that's a quantity of my interest. So I am differentiating four quantities Ct, x, y and z. So by differentiating all these quantities with respect to dt dash, we obtain C being constant. It is out of that differentiation sign. And here we have dt upon dt dash, that can be written as gamma, which is coming common. C I have taken inside the bracket. Then dx by dt dash, I have used chain rule to write dx by dt and dt by dt dash, so that we have common gamma here, and dx by dt is x component of velocity. So on and so forth. This is y component of velocity. This leads to gamma. This is z component of velocity, and this leads to gamma. So gamma I have taken common. Inside bracket we have c, vx, vy, vz. Now if you like to define 4 momentum, it will be proper mass into proper velocity. So proper velocity, I'm talking about 4 velocity, as we have started with 4 position. So this will be simply m0 times velocity that just now we have derived. So in all we have this m into m0 into gamma. I'm writing as m, because relativistic mass is equal to gamma times m0. So here I'm writing mc, mvx, mvy, mvz. So this quantity, mass into velocity of light, I'm calling p0. And these three quantities are our usual three momentum, that is small p bar, you can say. Now we shall take a dot product of 4p with respect to 4p, that will lead to, by definition, p0 minus mod of p bar square. So this small p bar is 3 momentum, and capital P we are calling 4 momentum. So 4 momentum into 4 momentum, we have p square into 3 momentum square. So m0 gamma c whole square minus m0 v m0 gamma v whole square. This leads to m0 gamma c whole square we have taken common, and inside bracket we are left with 1 minus v square by c square. So this can lead to 1 upon gamma square by definition. So here you can see this. So this gamma square into this gamma square, 1 upon gamma square, will be cancelled and will be left with quantity m0c whole square. So when we are taking dot product of x with respect to x, I'm talking about 4 momentum. When we are taking dot product x dot x, we are left with something which is constant that we call interval. And when we are taking 4 momentum into 4 momentum, we end up with a constant m0, which is proper mass involved into velocity of light whole square. So this quantity is invariant, the same. It is the same for all inertial observers. Invariant. Now P0 I have defined as m into c, that we can write E by c. Here I am presuming that we already know E is equal to mc square. This is the only presumption I am carrying forward in 4 vectors representation of special relativity, and then everything fits very well. This is the only presumption I am taking, but I am going to get lot many advantages of writing 4 vectors. I mean relativity using 4 vectors. So P0 is equal to E by C. Now we can write this P4P dot 4P equal to P0 square minus mod of P square. This is equal to E by C whole square minus P square. And we have seen that P dot P, this is equal to M0C whole square. So here we are ending up with the equation M0C whole square is equal to E by C whole square minus P square. This is the most important equation that we are interested in. And here this small p square is actually mod of small p bar square, which is in fact px square plus py square plus pz square. So this I'm substituting here. So here we end up with the most important equation, which is outcome of spatial theory of relativity, that m0c whole square is equal to e square by c square minus px square minus py square minus pz square. In the last slide, we have taken p0 is equal to mc whole square. So this can be written as m0 gamma c whole square. Now I want to pass a very important remark. P0 is equal to m0 gamma c, that we can write as E by C, with the only presumption that we are taking E equal to mc square. So we can write E by C equal to m0 gamma c, and E by C we can write m0. I have expressed this gamma from this relation and that multiplied by c. So in the numerator we have m0c, and that is multiplied by 1 minus v square by c square whole to the power minus 1 by 2. We can make a binomial expansion of this, and v square by c square is very small, and then the next term v to the power 4 upon c to the power 4, this will be yet more closer to 0. So we are ignoring higher order terms, and we can write E is equal to m0 into 1 by 2 m0 c square into 1 by 2 m0 v square. So this leads to the rest energy. This part is rest energy, and the another part, this one, everyone knows it is kinetic energy. So here we have concluded another important thing, and now I am switching to the quantum mechanics part. The starting point of our discussion here is the Schrodinger's equation. Klein-Gordon equation is the kind of stepping stone between the Schrodinger's equation, which is non-relativistic, and Dirac equation, which is relativistic, that captures spin of electron. So Schrodinger's equation is non-relativistic, Klein-Gordon is relativistic, and Dirac is relativistic, that offers you information about spin of the particle. Schrodinger's equation is applied to quantum physics. Klein-Gordon also applied to quantum physics. Dirac's equation is for fundamental particles fermions. Then the Schrodinger's equation is applicable to quantum mechanical problems, whereas Klein-Gordon equation offers unification of space-time energy momentum, and Dirac equation offers antimatter information. Schrodinger's equation is unfashionably Newtonian, whereas Klein-Gordon is relativistic but with no spin, whereas the Dirac equation unleashes the horror of spinors. Schrodinger's equation is philosophically unsatisfying, whereas Klein-Gordon equation only subtle hints of antimatter, whereas the Dirac equation is going to change our life. and will never be the same. So let us begin our derivation with the principle from special relativity. In particular, we'll start with the mass shell. The mass shell is what determines the relationship between energy, momentum, and mass. That's the relativistic part of our relativistic wave equation. Now, on the wavy part, we are going to take our quantum mechanical energy and momentum operators, and that is the energy operator and momentum operator. So here you can look at the mass shell m0c whole square is equal to E by c square minus p square. So in place of E we are going to take energy operator, and in place of p, or rather p square, we are going to take momentum operator. This p is 3 vector, small p is 3 vector that we can write as px square plus py square plus pz square. The derivation of Klein-Gordon equation is in many ways very reminiscent with the derivation of Schrodinger's equation, except now we are going to use mass shell instead of p square by 2m. This is the mass shell we are going to use instead of p square by 2m. Alright, let's go ahead and write these equations. So we can see how the mass shell transforms into Klein-Gordon equation when the energy and momentum terms are written in terms of the quantum operators. So the energy operator, we know that E cap is equal to IH cross del del T operated on the wave function psi that offers eigenstate which corresponds to energy, and in this equation we are interested in looking at the term E square by C square. So E by C whole square we can obtain from this by double operation that gives a operator minus h cross square upon c square into del 2 by del t2. So we have to replace E square by c square by this operator. Then momentum operator. The momentum operator, I'm interested in this form p square. So p cap is minus IH cross into del bar. When this is operated, you get eigenstate of momentum, and when you look for p square, you have to reoperate that. So minus px square can be obtained by h cross square into del 2 by del x2, so on and so forth for y and z component, and the total p square. Here actually I am interested in minus p square. So minus p square from this equation you can write as minus px square minus py square minus pz square, that is equal to minus h cross square plus del square. Now I want to use this very equation to write in terms of operators. So here this E by C whole square is replaced by this quantity. Then minus P square is replaced by this quantity plus H cross square del square, that is equal to the mass shell M0C whole square. So M0 is the rest mass upon which all inertial observers agree upon. So we can collect the proper terms together here, and I want to mention that you can divide the whole equation by h cross square and write h cross square here inside the bracket in the denominator. So m0c upon h cross whole square, everything is adjusted, 1 by c square del del t del 2 by del t square minus del square plus this term operated on wave function psi, this offers equal to 0. This is actually the Klein-Gordon equation. Now the D'Alembert operator is used here, which is in place of 1 by c square, this quantity 1 by c square del 2 by del t2 minus del square. So in place of this, we are using D'Alembertian operator. So this is a very interesting phenomenon. I want to relate in terms of notations. So when we are talking about three-dimensional del operator, this is relating to three dimensions x, y, z. And when we are adding a time dimension along with this, so this triangle with four sides, we are replacing by a square. So this del operator, and here we are substituting the value of mu as m0c upon h cross, so that our Klein-Gordon equation is D'Alembertian operator plus mu square operated on wave function psi. So if you substitute rest mass of electron here, then you can obtain the value of mu to be 2.59 into 10 to the power 9. So this is what is the Klein-Gordon equation which we were interested in deriving. Let us explore this in terms of solution now. The Klein-Gordon equation you can observe on your screen, which is having a D'Alembertian operator, and the Klein-Gordon equation really is the square plus mass squared. So here I'm talking about mu equal to m0 c upon h cross. Now here c is absolute constant, h is also a constant, so mu is directly proportional to mass of the object. So proper mass m0 is determining the value of mu. The elegance of this equation is not a coincidence if you go back to the simplest definition of the mass shell, which is the 4 momentum dotted with itself equal to m0 c whole square. Then if you also unify the energy momentum operators into this thing, that the 4 gradient of the wave function up to the factors of I and h cross. So here this del bar operator with a suffix mu, where it is different from this mu, and I want to write this mu as a suffix rolling from 0, 1 to 3. I'm talking about this mu, and this del bar operator I was talking about is 4 gradient. Thinking in terms of triangles and squares, then you'll see that there's actually a lot of elegance and simplicity here, even more so than was evident in our derivation. So what do the solution of Klein-Gordon equation look like? Let's begin exploring the solution. Now here we are going to discuss the Klein-Gordon solution, and to discuss solution I have rewritten the Klein-Gordon equation. This is the compact version in terms of D'Alembertian operator, where mu is m0c upon h cross, and the D'Alembertian operator is like this, and this is the relativistic mass shell. Now the solution we propose as a into exponential of minus I upon h cross 4 momentum p dot 4 position. Now we have to explore this. 4 momentum we write as mc, mvx, mvy, mvz. In general we can write that as p0, p1, p2, p3, and in general we can write this as p mu, where this mu is having values 0, 1, 2, 3, and it is different than this mu. Similarly, x can be expressed as 4 position ct, x, y, z. In general, we can write that as x mu. And the compact version of representation of 4 momentum is equal to P0 3 momentum. So P0 is the first element, which is MC, and P bar we are writing in place of this. In place of this we are writing P bar. And similarly, the 4 position is equal to CT into 3 position, that is R bar. Now A is belonging to the set of complex numbers. P, as I said, it is Px, Py, Pz, and if you like mod of P, it is under root of Px square plus Py square plus Pz square. And P0 we write as E upon C, that is equal to plus minus under root of P square plus MC square. Now, overall, P dot X we can write P0 X0 minus P bar dot R bar, and P0 we can write as E by C, and X0 we can write as CT. So E by C into CT, it will be E into T, CC will be cancelled, and minus P bar dot R bar. So overall, we can write the solution psi equal to A times exponential of minus I upon H cross Et minus P bar dot R bar, where this is 3-dimensional momentum and this is 3-dimensional position. If you like to write in terms of 4-dimensional momentum and position, you can write like this. Now, probably if you are learning this subject for the first time, the solution that we are going to offer is in terms of 4 vectors, that is dot product of 2 4 vectors that leads to a scalar quantity, obviously. Now here on the left corner, you can observe the Klein-Gordon equation in the form that we are going to use. This is the compact version of the Klein-Gordon equation with D'Alembert operator. Here you can observe the solution in terms of 4 vectors, where we are considering 4 momentum P bar dot 4 position vector. And if you expand this, it offers this quantity. I'll explain you quickly how it occurs. So 4 momentum we can write as P0, P1, P2, P3. In general, P mu, where mu can roll from 0 to 1. Similarly, the 4 position is x0, x1, x2, x3. In general can be expressed as x mu, where again mu rolls from 0, 1, 2, 3. Now P dot x we want to work out. It will be P0 x0 minus P1 x1 minus P2 x2 minus P3 x3. Here I want to tell you that the quantity we are going to consider here negative. This sign is positive, this is negative, and this is negative. This is plus, minus, minus, minus. This is result of Minkowski matrix, and that is nicely embedded into the definition of 4 vectors. So this offers you P0 x0 minus P bar dot R bar, where P bar, small p bar, is a 3 momentum vector that we usually discuss. And this 3 momentum vector we write as P bar equal to Px I cap plus Py j cap plus Pz k cap. Similarly, the vector R bar we write as some position x times I cap plus y times j cap plus z times k cap. So P dot R you can obviously imagine. Now we are interested in minus I upon h cross into P dot x, that is 4 momentum dot 4 position. So it will be I upon h cross P dot R minus Et. So minus sign I have adjusted that you can relate. D'Alembert operator operated on wave function psi. So D'Alembert operated on exponential of I upon h cross p dot r minus et. D'Alembert I am replacing by 1 by c square del 2 by del t2 minus del square operated on the wave function exponential I upon h cross p dot r minus et, where conveniently I have ignored this amplitude of the wave function a is equal to 1 without loss of generality. Now we shall perform the operation 1 upon c square del 2 by del t2 operated on this wave function minus del square operated on the same wave function. Now here e to the power function, the derivative will be e to the power function into f dash. So here second order derivative will offer us minus I e upon h cross, which is in multiplication with the time. Your operating derivative with respect to time, it's square because of second order derivative times the same function, minus I h cross upon p, I p upon h cross square, because this del square operator is being operated on this quantity where time is being treated constant. This square because of second order differential equation. So here you can rearrange the terms together. Here minus square will be plus and I square will be minus 1, and that minus I have taken common out. Then this I square will be minus 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 plus. So as minus is taken out, we are having inside minus sign. So we are left with e by c square minus p square upon h cross whole square. This is equal to minus mc square, sorry, m0c upon h cross whole square. This is attributed to a letter mu for shorthand notation. So the Klein-Gordon equation really satisfied by the solution that we have considered, psi is equal to a into exponential of I upon h cross for momentum dot for position. The super concept of superposition of wave functions. The superposition of wave functions that satisfy Klein-Gordon equation also satisfies the Klein-Gordon equation, and that lets us create a complex landscape starting with the basis set of functions. Let's say you have two wave functions that satisfy Klein-Gordon equation. Let's call them psi1 and psi2. So both psi1 and psi2 satisfy the Klein-Gordon equation. This is the Klein-Gordon equation in the compact form. This is the expanded form, and this is the wave function psi. And here we propose psi1 and psi2 both satisfy the Klein-Gordon equation. Let's call their sum psi3, so that psi3 is equal to psi1 plus psi2. The question then arises, does psi3 satisfy Klein-Gordon equation? Well, yes, it does. Here you can see we have operated the Klein-Gordon equation on psi3, and actually psi3 is replaced by psi1 plus psi2. Therefore, independently, both are satisfying the Klein-Gordon equation. So this results to 0, this results to 0, and the sum 0 plus 0 is 0. The crucial insight here is that because the D'Alembert operator is a linear operator, it does satisfy. The similar reasoning applies to a set as appearing on your screen. Not just the sum of two wave functions, but also to the scaling up of a wave function, or taking arbitrary sum or many wave functions, or even more usefully, if you have a basis set of functions that satisfy Klein-Gordon equation, then you can make a wave function out of that basis set by summing over them with some series of coefficients. That's how actually use energy and momentum eigenstates most of the time. So think of these Klein-Gordon plane waves as being thread that we can use to wave together for all kinds of more complicated landscapes. So here psi1, psi2, psi3 up to psi n are the wave functions that satisfy Klein-Gordon equation, and Cn is a set of complex numbers. So the linear combination Cn psi n, sum of all, that we represent as a linear combination of psi n's, and that psi is subset of psi n, and therefore you can write, as all psi-n's are independently satisfying Klein-Gordon equation, you can very well write their linear combination also satisfy the Klein-Gordon equation. So we are in position to talk about phase velocity and group velocity. I am beginning our discussion with wave function psi, which is equal to amplitude times exponential of I upon h cross p dot r, 3 momentum into 3 position minus energy into time. And this mass shell equation I have rearranged for energy E. So in order to calculate the group velocity of the Klein-Gordon equation wave packet, we first calculate something called the dispersion relation. The dispersion relation is when the angular frequency of a wave function is written as a function of wave number. So to calculate the angular frequency of our plane wave, what we want to look at is the factor that is multiplying I into time. So I and time is being multiplied by omega, that is angular frequency, right? So the question is, what is omega factor? And by inspecting our Klein-Gordon plane wave equation, you can figure out the angular frequency, omega. Now, here, the general form of Klein-Gordon equation we are comparing with, and here, omega, which is being cited here, is resembling to this E upon h cross. I into t are the common multiplying factors. So omega is equal to E upon h cross, and this E is being substituted from this mass shell that is coming from special relativity. So C upon h cross under root of 3 momentum square plus m square c square, m0 square you can call, that is rest mass. So here we have k is equal to p upon h cross, or you can write p equal to kh cross. Substituting that in our last equation, we can write omega dispersion relation, which is function of k. And here you can observe that omega is equal to under root k square c square m0 square c square upon h cross whole square. So these are dispersion relation which we are going to explore in the next slide. Now here I have rewritten the equation, which is actually omega, and then group velocity is d omega by dk. So I want to differentiate with respect to k this very first relation. So when we want to differentiate with respect to x, any function which is under root of something, we write it as 1 upon 2 under root of function, and then multiply the denominator by derivative of that function. So same thing I am doing here. You can figure it out by pausing the video, and here we conclude that Vg is equal to mod of Pc upon under root of mod P square plus M0 C whole square. So here mod P is actually magnitude of 3 momentum, and you can write this as under root of px square plus py square plus pz square. We are doing it every now and then. So Vg, group velocity, is equal to c times mod p upon under root of mod p square plus m0c whole square. Now, when the rest mass of the particle m0 is equal to 0, then this term will vanish and will be left with only c. In that case, Vg will be only equal to c. And when m0 is greater than 0, Vg, you can figure out, will always be less than 0. So this is the relation for group velocity, that is velocity of the wave packet when mass m0 is equal to 0. So we are talking about massless particles, say photons, then the group velocity is c. And for any matter particle where m0 is not 0, the group velocity has to be less than the velocity of light. So while playing around the Klein-Gordon equation, we have found the speed limit, that is speed of light. Massive particles only can approach the speed of light as the momentum increases, and it never reaches to the value of velocity of light c. Massless particles always travel at c regardless of their momentum. This is an essence of relativity. Here you can observe a material particle of mass m moving with increasing velocity. It approaches the velocity of light, whereas the massless particle, you can observe, moves with velocity of light irrespective of its momentum. In the last slide, we have concluded that the massless particles will travel at the speed of light, and this is like essence of relativity, and at the same time it's all wavy and quantum mechanical also. So what's the problem? Why Dirac was not satisfied with the Klein-Gordon equation? Well, to answer this question, we have to go deeper. So the math is about to get a little bit of fancy. Imagine we have a particle that doesn't have definite, precisely known 4 momentum, but instead it's kind of smeared out on the mass shell. So here I'm just showing you one-dimensional momentum. Let's say it is along x direction only and ignore y and z component. And I'm also showing you the energy. This on the vertical axis. So here I'm showing you a particle that occupies a bit of mass shell. So to get visual intuition, if you'd like, you can draw out probability dimension and think of this as a bell curve. What does the wave function in space-time look like for such particle that has kind of momentum distribution And well, if you think about it, actually, the information that we have here is not quite enough, because we can think of some momentum distribution as superposition of infinitely many specific momenta. So we can say this distribution is just like infinitely many eigenstates stacked on the top of each other, and each of those eigenstates is going to have some weight. And so to calculate the wave function in space-time, all we have to do is take a weighted sum of all eigenstates corresponding to each of the momentum points, right? But when you do that, you have to calculate the integral. And it's an integral because it's just a sum of continuous limit. So here you can observe the mass shell equation, and we have rearranged it in the form x square minus y square equal to 1. And here psi of x is a wave function in free space and time, and phi of p is a complex numbers on mass shells. And here what we need is a one-to-one correspondence between psi of x, capital X means 4 position, psi of 4 position, and phi of 4 momentum. We need to have a one-to-one correspondence, we need negative shells for complete basis set. This was the problem. So this has given a setback to Klein-Gordon equation about the upcoming of negative shells, which corresponds to negative energy. Klein-Gordon equation predicted antimatter would really be an overstatement, because the time it was published, back in the day of late 20s, people were not thinking in terms of antimatter anyway. So that's one critique when it comes to Klein-Gordon equation. The facts that it has all of the problems with negative energy situation, and yet it doesn't offer us a redemption of teaching us about the antimatter. Another fundamental critique on Klein-Gordon equation is that it is second order in time. Now you think back to Schrodinger's equation, which is first order in time. When you have an equation that is first order in time, then you all need to know at any moment is the situation with the wave function. What is the wave function like in any moment? And then Schrodinger equation says you can take a Laplacian and do something that gives you the time evolution of the system, right? But you don't have to specify the rate of change of wave function. All you need is only wave function. As you consider the case of Klein-Gordon equation, which is second order in time, it opens up another kind of degree of freedom, which is okay. But what is the rate of change of wave function is to be known, because when you have an equation of second order, then the first order derivative in time becomes an initial condition. So this was the second problem. So first order and second order was the issue. Then when you calculate probability densities that arise out of Klein-Gordon equation function, wave function, you see that sometimes the probability densities can be negative. Here in this equation, it is quite possible that the probability density can be negative, which has received a great setback. People accepted that at that time about the negative values of probability density, but Dirac had a very serious objection on negative probability densities. Very quickly, I want to bring it in front of you how the negative probability density was calculated that time out of Klein-Gordon equation. Here we have Klein-Gordon equation operated on a wave function psi, and we are taking complex conjugate of the wave function. D'Alembert operator and mu are not affected by the complex conjugate. So multiplying the first equation by minus psi star on both sides and multiplying the second equation by psi on both sides, and then you can add them together so that you can cancel out the term associated with mu square, and we are left with psi D'Alembert operator psi star minus psi star D'Alembert psi equal to 0. D'Alembert operator can be expanded from this definition: 1 over c square second order partial derivative with respect to time minus Laplacian operator. This is to be operated, and by operating that and simplifying and collecting terms together, we can write the equation, and we can multiply both sides by IH cross upon 2m, and then we arrive at this equation which is appearing on the right hand side. This equation is very similar to continuity equation which we have encountered in physics at many places, including fluid mechanics and electromagnetic field theory. So here we have the resemblance with continuity equation where you can find out probability density rho and the current density J. So this is that value we have used in the earlier slide. So here the value of probability density can be negative. Is it correct? Dirac had a very serious objection on this. So I want to conclude here that psi star into time derivative of psi, when this quantity is greater than psi into psi star time derivative. In this situation, the probability density is negative, and negative probability density is difficult to interpret. Dirac was really not a fan of this equation. Last but not the least, Klein-Gordon equation does not speak about the spin of electron. It is not acceptable that the relativistic electron has no spin. Electron, proton, neutrons all are spin-half particles, aka fermions. Spin is an integral part of reality. Physicists knew that electron had spin-half, that is, two spin states, before the nature of spin was understood because of the duplexity phenomenon. For example, a way back in 1896, Zeeman effect was showing us two spectral lines. Stern-Gerlach experiment of 1922 was giving a beam splitting, that is two beams, various chemical things, two electrons per orbital. Why two? So spin has to be an integral part of our equation. That was foreseen by Dirac, and his objections found a strong list, though physicists that time did not pay attention to these issues, but Dirac was not satisfied with Klein-Gordon equation, that is for sure. Today we have a very modest and a very well defined goal to derive Dirac's equation, and you can very well see where it comes from. It has three ingredients, that is, the first thing is the mass shell. So here I'm going to prefer m0, I'm going to replace by m, and you understand that now onwards this is proper mass. Okay. So for simplicity, I am choosing this notation. And here you look at this equation, which is kind of hyperbola. If you are having E by C on y-axis, it will be y square minus, I'm considering one-dimensional equation, for example, then this is x component, I'm calling x square. This is equal to some constant, say alpha square. So this is the equation of hyperbola which opens up and down. So I want to draw the hyperbola now. So this is that hyperbola which is symmetric about your x-axis, and this point is, you can call alpha, and this point you can call minus alpha, and this is y square minus x square equal to alpha square. So this equation you are very well familiar with, and this mass shell we are going to use, and then we are considering for momentum capital P suffix mu, where mu is ruling from 0, 1, 2, 3. For time, space 1, space 2, and space 3, that is x, y, z. IH cross partial differentiation with respect to that variable. Once with time, second time with x, third time with y, and fourth time with z. And then you have uh, separated energy and momentum operators. And when you try to put that here, you need to Klein-Gordon equation. And this was the third ingredient, was the most important ingredient that Dirac had. He wanted a first order equation in space and time. The moment we try to specify that the equation should be first order, and here you are encountering with squares, so obviously you encounter with second order derivatives. So what Dirac did, he did a very simple thing, but that is going to lead to a bizarre mathematics. So he took square root of energy shell equation, you can see. So mc is equal to under root of the whole quantity by c whole square minus px square minus py square minus pz square. Now he proposed that the root of equation he should be able to express as some constant a times e, b times px, c times py, and d times pz. Now finding this is not that simple, because we want to find out a, b, c, d, and all other terms involved should be zero. That is going to lead to some bizarre mathematics that you can understand. Now here again taking square on both sides of last equation, and now here we have to handle this equation so that we should be able to find out what is a, b, c, and d. The moment we do that, we end up with the Dirac's equation. Now I have rewritten this equation. Here I want to propose that the velocity of light without loss of generality, we shall consider c equal to 1, and then I shall reinstate the value of c uh, in our usual way. And the another thing I want to highlight that we are treating uh, m0, that is rest mass. Now when you square this term, you will end up with 16 terms, and those 16 terms you can see in this tabular form. So you can work out these 16 terms. Now I would like to rearrange these 16 terms in the way my mathematics permits. That is, a into e whole square, I am writing a square into e square. B into px whole square, I am writing b square px square. C py whole square is equal to c square py square. D pz whole square is equal to d square into pz square. Likewise, I am writing another terms. And what do we expect here? To match with this equation, look at this term as e square only. To match with this, I want that sorry, this a square should be 1. This b square should be minus 1. This c square should be again minus 1. And d square should be minus 1. What else I want? This ab e into px plus ba into e into px. This is equal to 0. Similarly, this term and this term should vanish. This term and this term should vanish. Then this term and this term should vanish. Similarly, this term and this term is expected to vanish, and this pair of terms should vanish. And we can collectively write a couple of equations. That is, a square should be 1, b square equal to capital C square equal to capital D square equal to minus 1, and few more equations which are coupled together. So in the next slide, I'm going to write that. So what we are expecting is on the left hand side chart, where we want e square minus px square minus py square minus pz square. This is what we anticipate. Rest other terms we want to get vanished. And this is out of the equation, which is the first equation highlighted here. Now, the expectations that we have are a square equal to 1, b square, c square, d square all are minus 1. Then ab plus ba, this constant, should have this relation ab plus ba equal to 0. AC plus CA is equal to 0. AD plus DA is equal to 0. BC plus CB equal to 0. And BD plus DB equal to 0. And the last equation, CD plus DC equal to 0. This is what we anticipate from the root of the equation that we were trying to find out, and we are yet to find out what are the values of A, B, C, D, and which mathematics is going to support us for this. So the whole game was finding root of this equation, and in order to find root of this equation, we had 10 equations constraining us. Out of 10, these are the 4 equations. The next bunch of 6 equations is like this. The set of equations which are in front of you that tells you a kind of relationship AB plus BA equal to 0. It means that it is not commutative. And you have a whole bunch of such 6 situations. So at the first place, real numbers are not going to behave like this. And obviously complex numbers also are not going to behave in the same fashion, because both complex and real numbers are commutative. So what we need for representation of A, B, C, D is more exotic. Now in case of cross product, I would like to write something. In case of cross products, for example, we have A bar cross B bar. That will be equal to minus B bar cross A bar, and this kind of relationship can be satisfied, but this is a very limited approach. So this gives a kind of example that you can find, but in matrix algebra you can find out such many possibilities. Dirac found such 4 by 4 matrices as solution, and there are many other solutions in matrix algebra also that you can track. Youngsters can try that. However, Dirac's matrices is one way which people consider to be one of the most standard way, wherein we have A now being represented by gamma 0 for further notation, B being represented by gamma 1, C being represented by gamma 2, and D being represented by gamma 3. So actually we are having a kind of equation which can be generalized as this highlighted equation, MC equal to gamma mu p mu, where mu rolls from 0, 1, 2, and 3, and this is that equation which is known in the literature as Dirac's equation. So this 4 by 4 matrices can be clubbed together for a shorthand notation for this type of matrices, where we have shorthands as a unitary matrix, then this one as Pauli's first, second, and third matrix. So bear with me, this is the last slide of the long discussion that we are having and that is leading to spinors now. So here we have Dirac's equation, gamma to the mu. Actually, it is a notation not to the power. Gamma mu p mu equal to mass shell mc, and p mu we can write as IH cross del mu. So this mu is a number that is rolling from 0 to 3, and when we are talking about del 0, it means that partial derivative with respect to time. Del 1 is partial derivative with respect to x, so on and so forth for other two. And then I'm going to represent p mu here by the operator. Now we can shift to the notation of del mu. We are dividing the equation by IH cross, and by virtue of that, this will be also divided by IH cross. Here we are dividing by IH cross, and you can cancel out this IH cross, and this I can be taken up with a minus sign, so it will be minus MC I times divided by H cross. So this can be rearranged further like this, and we can open up the notation for gradient in this fashion, and psi for this matrix algebra that we have discussed, where A, B, C, D we have represented by gamma 0, gamma 1, gamma 2, gamma 3. We need psi to be a column matrix, psi 1, psi 2, psi 3, psi 4. So first two coupled together makes psi 1, and last two coupled together makes psi b. So this is psi a and psi b. So psi a and psi b are spinors, and the highlighted equation is another form of Dirac's equation. So psi 1, psi 2, psi 3, psi 4, they belong to the set of complex numbers, and psi 1 corresponds to spin up uh, electron, psi 2 corresponds to spin down electron, psi 3 corresponds to spin up positron, and last one for spin down positron. So I conclude here. I hope you got interested in this video, and I would request you to like, share, and subscribe. this video.